Welcome to OCR A-Level Physics 2019 Paper 3 Unified Physics. And because OCR are cool dudes, they let me show the paper on screen unlike another certain board. Question 1, we have a toy rocket, 1.5 litre plastic bottle. It contains that many litres to begin with, leaving that much trapped air, fine, at 17 degrees. Guaranteed we're going to have to turn that into Kelvin. Do you know what? Let's do that right now. So 17 plus 273, that gives us 290 Kelvin. 1 litre is thousandth of a metre cubed. Alright, what are we being asked first? Calculate the number of moles of trapped air. Oh, forgot we have a pressure there. Cool, so we're going to go for PV equals nRT. We're looking for N, so N is equal to PV over RT. So that's going to be our 2.4 times 10 to the 5 times the volume. That was 1.2 litres, but we know each one of those is times 10 to the minus 3 meters cubed. And then we divide that by our gas constant times the temperature, but it has to be Kelvin. Powers of 10, might as well. Take away 3 from the 5, so we just end up with times 10 to the 2, so basically 240 times 1.2 on top. 240 times 1.2 divided by 8.31 times 290. That gives me 0.1195 moles, or to 2 sig figs, because our data is given to 2 sig figs, 0.12 moles. Fairly easy start. Trapped air pushes the water downwards, blah blah blah. Calculate the final pressure of the trapped air just before all the water has been released. Okay, so we know that the volume is going to expand to the full 1.5 litres afterwards. Actually, we don't need to turn that into meters cubed. Why is that? Well, let's just have a look. PV equals nRT. What's staying the same? The number of moles is. Obviously, the gas constant is as well. We're told the temperature remains constant as well. So therefore, we can say that P1V1 is equal to P2V2. We're looking for the final pressure, so therefore, that is going to be equal to P1V1 divided by V2. So, what was our starting pressure? 2.4. Do you know what? We can just say 2.4 because it's all relative. We just know that our answer is going to be times 10 to the 5 in the end. So times that by the first volume, that was 1.2 litres, and then it's expanding to 1.5 litres. Again, if you put the times 10 to the minus 3 on both of those, they cancel, so there's no point. And that gives me 1.92, but we should probably go to 2 sig figs. So 1.9, but we know that that was times 10 to the 5 pascals. Here's some data. We have the mass, we have the cross-sectional area of the hole, we have the initial pressure, we have atmospheric pressure, fine, and we have the density of water. Oh boy, what are we going to have to do here? So use the data above to show the upwards force on the rocket at the start of the liftoff is about 15 newtons. Okay, so if we're looking for the upwards force, we know it's going to be something to do with pressure. So we know pressure is equal to force divided by area. But if this is our bottle here, then we know that we have the air pushing down there outwards, but then we also know that we have air pushing the water back in as well. Not as much, but the point is that we can't say the pressure pushing downwards is that 2.4 times 10 to the 5. So we have to say that the resultant pressure, or the total pressure, we might call that the difference in pressure. It's just going to be that 2.4 take away the 1 times 10 to the 5 for atmospheric pressure. So in other words, that gives us 1.4 times 10 to the 5 pascals. So therefore, force is equal to pressure times area. So that's going to be our 1.4 times 10 to the 5 times cross-sectional area, which is 1.1 times 10 to the minus 4. These cancel, so we just end up with basically 14 times 1.1. And it does look like that's going to be about 15. That gives us 15.4 newtons. So that's similar to the Boyle's law experiment they might have done with the syringe. You have to take into account the difference in pressure because we have the atmosphere pushing back as well. Calculate the initial vertical acceleration of the rocket. Okay, so we know we're going to have to use F equals ma, but again, remember that, well, m is total mass, fine, but this is also resultant force. So we have our rocket. Let's draw our forces on there. We have our thrust pushing upwards. I'm going to call that T. Of course, that is resulting from the force that we just calculated. But then we have weight pulling downwards as well, mg. So therefore, the resultant force is equal to the thrust take away the weight. The weight is hindering, it's accelerating as it were. Therefore, just putting m over the other side, you can see that t over m, and of course the m cancels for the mg, so just minus g gives us the acceleration. Now we know that the thrust was that 15.2. You might be tempted to say that the mass is that 0.05 kilograms. However, that is the mass of the empty bottle and the fins. We of course have been given density as well, so we know we're probably going to have to use that at some point. Indeed we are. How much water was in there? Well, it was 0.3 liters, and we know that that is 0.3 times 10 to the minus 3 meters cubed. If we then times that by 1,000, that gives us 0.3 kilograms. That's just the way it works. You probably know that a litre of water has a mass of 1 kilogram. So therefore, the acceleration is going to be equal to the thrust. That was our 15. Let's go with 15.2 divided by not 0.3 but 0.35, because we're adding on the bottle and the fins, and take away 9.8. And that gives us 33.6, or let's go to 2 sig figs, 34 meters per second squared. Not a super easy question, that one there. D, discuss whether adding more water would enable the rocket to reach a greater height. Again, not an easy question this. Let's have a think about the air for starters that was in there. So that would mean that we would have less air. But if we're assuming that the pressure is the same, thrust would not change, at least initially. However, mass would increase, therefore, resultant force would change. It would decrease, and therefore acceleration too. But as more water, rocket accelerates for a longer time. So actually, it's very difficult to predict. So that's actually really cruel to have this as a question, but they're just expecting you to just talk through the various factors that would affect the height that it reaches. So let's just add into here mass increase, therefore resultant force would decrease, and acceleration too. So we would say lower height reached, but then rocket accelerates for longer time, therefore we'd say a higher height reached. But how much each of those affects the height reached, well, we'd have to do some fairly beastly calculations to figure that out. We have to know exactly how long it's accelerating for, blah blah blah. So yeah, really not a nice question, OCR. 2 cobalt-60 is made by irradiating cobalt-59 with neutrons. Nucleus then decays into a nucleus of nickel by low energy beta minus particle, one other particle and 2 gamma photons. Right, so we're being asked to sort this out then. So a neutron mass is 1, proton number, atomic number is 0. Next, what do we have? Well, we have an electron over here. We know is beta minus, so this electron is going to be 0 mass, effectively, minus 1 atomic number. Nickel, well, just having a look at the mass, it's going from 60 to something and 0, so the mass is going to be 60. We know that's true for beta minus decay, don't we? And we know that we have a neutron turning into a proton. So that means that we have an extra proton. And the numbers add up, don't they? 28 plus minus 1 gives you 27. And we know that we must have an anti-electron neutrino made as well by beta decay. Students wanting to carry out investigation, blah, 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 blah. The source emits beta radiation as well as gamma radiation. Explain why this would not affect the experiment. Beta particles would be absorbed by the lead. Yes, we know that the gamma radiation is attenuated, or the intensity is reduced by the sheets of lead, but it's not completely stopped, is it? But the beta particles would be immediately stopped by the first sheet of lead. Student recalls a number n of gamma photons detected by T in 10 minutes. Okay. Oh, we have uncertainties. N and D are related by the equation that, students decide to plot a graph of n against D. Show that this should give a straight line with gradient minus mu and y-intercept log n0. Okay, so first things first, we need to take natural log of both sides. Oh, I guess I should probably rearrange it first. There we go. Next we take logs of both sides. That just gives us minus mu d. If you know your log identities, you should know that the log of two things divided by each other is the same as the logs of those individual things taken away from each other. That gives us minus log d. Therefore, log of n is equal to minus mu d plus log of n0. Therefore, we can just say y equals mx plus c. There we go. Mu is the gradient and log n0 is the y-intercept. To complete the missing value of log n in the table, including the absolute uncertainty, show you a calculation of the absolute uncertainty in the space below. Okay, so first we're just going to get a log of n. So log of 300, that gives us 5.70. when it comes to any sort of weird operator like logs, or when you have reciprocals, that kind of thing, it's always best to, instead of going for the percentage uncertainties, actually go for the limits. So we're going to do 300, let's say plus 340. So let's do the log of 340, and that gives us 5.83. So therefore we can say the absolute uncertainty is going to be 5.83 take away 5.7. That gives us 0.13. So that's going to be our absolute uncertainty. Mark scheme says you could find the absolute uncertainty in your value for n and then apply that to the value for log n, but that will give you a much bigger value. So it's fairly obvious from these that that isn't how they've calculated it. We have a graph. Plot the missing data point and error bar. Why do they use dots? So what do we say? 5.7. Okay, so I can see that every two little squares is 0.1, so 0.56, 0.57. Then we need to go up 0.13 either side. Of course, you're going to be more accurate than I. Okay, we're being asked to draw a line of best fit, so just making sure that we have the same number of points on either side of the line. Well, that's actually not bad without a ruler. You, of course, are going to use a ruler. Then we need to draw a line of worst fit. Now, just remember with the line of worst fit that it does not have to hit the bottom or the top of the first and last error bars. It just needs to make sure that it's the most extreme gradient, either lowest or biggest gradient, that goes through every single error bar. But I think in this case, I think we are going to end up hitting the bottom of the first error bar. And of course, don't forget that your line of worst fit is always going to cross the line of best fit, even if it's just right at the ends, but it's never usually, it's in the middle somewhere. So we're being asked to determine mu, including the absolute uncertainty. So like we said, the gradient is equal to mu, or at least minus mu, but we don't care, it's just the magnitude, isn't it? And you should end up with a line of best fit gradient of about 54, and a line of worst fit of something like, I don't know, let's say 60. So therefore, we can say that mu is equal to 54 plus or minus 6. Just remember that if you gave your values to a higher degree of accuracy, say 54.0, then your uncertainty must be to the same number of, well, not sig figs, but the same decimal point, as it were. Determine the thickness, which halves the number of gamma photons. Fine. So we said log of n over n0 is equal to minus mu d. So if we're looking for half, we're looking for log of a half equals minus 54 d. So therefore, we just need to take the 54 over the other side. Make sure we have a minus in there as well. And it gives us 0.0128 meters. We should probably go to 2 sig figs, seeing that that's what our gradient was to. So 0.013 meters. Question 3, we have a mechanical torch. There's no battery. Instead, when the torch is inverted, magnet falls, blah, blah, blah. All right, so we have a bit of induction going on. Oh, isn't that clever? Can't imagine it lasts for long. Okay, we have the variation of EMF. Fine, explain the shape of the curve in figure 3. Right, so we know that just like when we have a magnet falling through a tube or a coil, it induces a magnetic field in the tube or the coil, but then by the time that the magnet gets to the other side, it has to flip because of Lenz's law. So as magnet enters coil, magnetic field produced in coil by induced current, the pole closest to magnet will oppose pole of magnet entering due to Lenz's law, because induced currents don't like being induced, so they try and stop being induced. So we have a north pole being induced that tries to counter the north pole entering. However, when leaving, poles flip, and so that means as does current, direction of current, as to oppose movement of magnet away from coil. So I talk about this all in my video when it comes to Lenz's law. So when the magnet enters, the coil goes, no, don't come in, tries to oppose it, so it makes a field that does that. But then when the magnet is leaving, the coil goes, no, come back. So it flips the poles to try and get it back. Induced currents are very fickle. They always want what they can't have. B, when the torch is inverted, blah, 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 we have a capacitance of that. Each positive and negative pulse, each positive and negative pulse, okay, adds that many coulombs to the charge stored in the capacitor. The torch is inverted 80 times. Calculate the energy stored in the capacitor. Okay, so we have a capacitance of 0.12 farads. That's huge. And we have a total charge of 9 times 10 to the minus 3 times 80. That gives us 0.72 coulombs. And so we're looking for an energy. So therefore we're going to use the equation half Q squared over C. So that is half times 0.72 squared divided by our capacitance. However, that doesn't give us the right answer. Why? Because apparently when you invert it, they're saying that you're doing it twice. So you're inverting it once and then twice. When you invert something, it just means you turn it upside down. So you're inverting it twice. Ugh! Bad OCR, bad wording. So it's times 80, but then times by 2. So that gives us 1.44 coulombs. Right, now we can do half Q squared over C, and that gives us 8.6 joules. When torch is switched on, energy stored is 50 milliwatts. Estimate the time for which the LED lights. Easy. Power is equal to energy divided by time. Therefore, just swapping these two round, we can see that time is equal to energy divided by power. So that is our 8.6 joules divided by 50 milliwatts. So in other words, 0.05. So in other words, 8.6 times 20. And we have 172 seconds, but we should probably do that to 2 sig figs. So we're going to say 170. So we have GPE, and it's turned into electrical energy, blah, blah, blah. We're asked to investigate whether the efficiency depends on the number of inversions of the torch. Describe how would you make measurements to collect your data. Assuming that both the torch and the tube can be opened, explain how would you use the data to reach a conclusion. Okay, right. So first of all, we need to calculate how much GPE magnet has, or we should probably say loses, as it travels. So we know that GP is equal to mgh, so therefore we need to measure mass of magnet with a balance, top pan balance if you want to call it that. Measure distance traveled with a ruler. So we can find out the GP, but then we need to find out the electrical energy that it's turned into. So we just saw an equation, power equals energy divided by time, so we can use that as well. So we can say calculate electrical energy with energy is equal to power divided by time. We already have the power, 50 milliwatts, so we can measure the time LED stays on for using a stop clock. I guess we should be accurate. We should say use dark room so we can see exactly when it goes out. Of course, we're going to repeat several times and calculate average, and then we're going to repeat the experiment with varying number of inversions, e.g. 10, 20, all the way up to, let's say, 100 times. And I guess seeing that we're asking us about efficiency, we know efficiency is going to be equal to the electrical energy out divided by the GPE. We should say total GPE. Of course, we do need to take our GPE and we need to times that by the number of inversions, don't we, in order to get the total amount of GPE. There we go, that'll about do it. Of course, we can times efficiency by 100 to turn it into percentage, can't we? We have baggage reclaim conveyor bolts. We have a constant speed of that. And we have a suitcase of mass of that. What are we being asked? Oh, okay, we have a slope. Using a vector triangle or resolving forces, calculate the magnitude of forces F and R. Let's do it properly. Let's draw what we know on here. We know that that's 30 degrees, so therefore this is 30 degrees in here as well. You should know that going down the slope is mg sine theta. If you don't know where I'm getting that from, have a look at my easy vectors trick video. And going into the slope, we have mg cos theta. And we know that this is going to be equal to R and this is going to be equal to F because it ain't moving up or down or into the slope or whatever. So therefore, we're going to say F is equal to mg sine theta. So that is, how heavy was it? 8 kilograms. 8 times 9.81 times sine 30. That gives us the 2 sig figs, 39. And then R is similarly that, but cos 30. So 8 times 9.81 times cos 30, and it gives us 68 newtons. Okay, but now it's going round a corner. Oh, how interesting. So it's like a bank track, but the opposite to a bank track. So we have the radius of the curve as that. We have the speed. Calculate the magnitude of the centripetal force acting on the suitcase. So centripetal force, of course, is just that going there. I'm going to call that C, centripetal force. It's the force that is going towards the center of the circle. Okay, so we've been given V now, so therefore we know centripetal force, tell you what, shall I call that C instead, because we've already got an F, is equal to mv squared over r. So that's our 8 times 1.5 squared divided by 2. So in other words, 4 times 1.5 squared, and that gives us 9 newtons. When the suitcase is at line y dash, the magnitude of force F is larger than the magnitude of force R. Magnitude of R is smaller than at xx. So we can say that at xx there is no resultant force, but at yy there is, as the case is accelerating. And we know it's undergoing circular motion, don't we? And here we are going around the corner. If you have F pulling up there, R pulling up there, so if this is theta, there's our centripetal force going that way, and that's theta as well. So basically up here there was no horizontal force, was there? Resultant, that is. So therefore we know that the horizontal components of F and R must be equal. So to begin with, horizontal components of F and R are equal and opposite, but at yy, can I just call it F horizontal must be greater than R horizontal, and we know that FH, so the horizontal components of one take away the other, is going to be equal to 9 newtons in order to supply that centripetal force. Not a super easy question, that one. It's sort of like the opposite to a normal backtrack. 5, hydrogen atoms excited, only emit 4 discrete wavelengths, blah blah blah. Semi-darkened room, we have 300 lines per millimeter. Do you know what? Let's turn that into a value for D already, shall we? So we know that's 3 times 10 to the 5 lines per meter. Therefore D is going to be equal to 1 divided by 3 times 10 to the 5, so that gives us 3.3 times 10 to the minus 6. Why is it always 3.3 times 10 to the something? Okay, we have a 15 centimeter plastic ruler. Oh, we don't even care about that, right? And we have 0.5 meters away. So here we have our first order for all the different wavelengths. We're being asked about the red one here. So how can you determine the wavelength? Estimate the percentage uncertainty in the measured value of the wavelength. Righty questions. So first of all, of course, we're going to use n lambda equals d sine theta. And we have our distance there, and we have the width that our order is away from the central max, from the 0th order, right there. Therefore, well, there's our theta there, so we can say that tan theta, because it's opposite over adjacent. Let's go with W over D, actually. Oh no, we got another D now. Let's call that big D. Just like our Young's double slit experiment. You know what? Let's do it. So therefore, theta is inverse tan of, what was it, 10 divided by 50 centimeters. As long as they're the same, it doesn't really matter. So we have 11.3 degrees. Fine, we've got that. We know that n is going to be 1, so that disappears. Therefore, lambda is going to be equal to, well, we found D earlier, 3.3 times 10 to the minus 6 times sine of 11.3. And it gives us 6.5 times 10 to the minus 7 meters. Now we're being asked to find an uncertainty. So we can say uncertainty in W is just going to be the same as the resolution of the ruler. So that's just a millimeter or 0.1 centimeters. Oh wow, no, now they're actually expecting us to do percentage uncertainty. Whatever, fine. They don't have pick and choose when they like doing this. So therefore, the percentage uncertainty in our value for W there is going to be just that 0.1 divided by 10 times 100. So in other words, just 1%. But now the mark scheme says that there's somehow 3% uncertainty in value for theta, and therefore tan theta and sine theta too. How? This makes no sense. Do you know what? Screw this question. I'm done with it. Sorry. Show the energy of photon, blah, 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 blah. I'm really annoyed now. So we have wavelength, we have energy. We know that E is equal to HF, but we have wavelength instead, so that's equal to hc over lambda. Oh wait, we're trying to find the energy, aren't we? Whoops. So that's Planck's constant times the speed of light divided by the wavelength. And that does give us bang on 4.09 times 10 to the minus 19 joules. Okay, we have discrete energy levels. Draw the arrow to show the emission of photon of that energy. So we're looking for a difference of 4.09. So it has to be from something down to the ground state, because anything like this is never going to give us enough energy. So let's just do 5.45, take away 4.09. And that should give us, by my estimation, 1.36. Sure enough, we have one there. So therefore, boosh, right down there. Describe the Doppler effect. To quote Sheldon off the Big Bang Theory, not that I watched that show, it's terrible. The apparent change in wavelength and frequency of a wave by an observer due to the relative speed to source. So how do we use a Doppler to find speed of blood flow? Pulses of sound emitted at flowing blood cells. Reflected waves have a different frequency due to movement of cells. This is then measured. Doppler effect, distant galaxies, blah, 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 blah. We have a loudspeaker and microphone. Oh, we're looking at, okay, so we have the radius there, fine. Loudspeaker, so we have frequency of that. We have the variation. Use figure 6.2 to show the speed of the loudspeaker is about that. So we know that V is equal to omega R, which is equal to 2 pi FR, which is equal to 2 pi R over the time period. So 2 times pi times the radius, which was 0.6 meters, divided by the time period, which is 0.5. Which ends up being, what, 4 times 0.6, so 2.4 pi. I think that looks about right. Speed of sound is that. Calculate the maximum change in frequency of the sound detected by the microphone. So again, we can just use that speed there, because it's going to be that speed when it's moving away. At any other point, it's going to be relatively not that fast. So we know the ratio of speed to just the speed of the wave is the same as the ratio of changing frequency to original frequency. So we're looking for this, so therefore delta F is equal to VF over C, so that is 7.5. Times that by our frequency was 1700 divided by speed, and it gives us to 2 sig figs 39 hertz difference. Hence complete the scale on the y-axis of figure 6.2. So it's going from 1700, how many squares are we going up? 1, 2, 3, 4, 5. And we know that has to be 39, but of course we're just going to say that's 40, aren't we? So that's 1740. And let's go down here as well, 1660. Mark with an X, position of the loudspeaker, which corresponds to point X on figure 6.2. Okay, so we've gone round not a full wave, because that's a full wave, so we've gone around 3/4. And so we're talking about when the change in speed is greatest. So I do believe that it's going to be there. Finally, D in their lab notes, one student writes about the accuracy of the measurements, whereas the other writes about their precision. Define these terms. Gosh, what a mean question, because they're so flipping subjective, because language is subjective, numbers aren't. So accuracy is how close a measured value is to the true value. That one's okay. We generally accept that. But precision, I really disagree with this term. I think that somewhere along the road over the last few years, everybody just started thinking weirdly, and precise used to mean something different. Precise, in my opinion, means, you know, how close are you? How precise are you? So you're being very careful, aren't you, with making sure that things are nice and, we can't say accurate, but whatever. But precise, the powers that be say that precise means how close values are that should be equal. In other words, when you're taking means, if all of your results are bang on the mean, then of course your results are very precise. But if they're quite spread out, then they're not very precise. I really disagree with that term, but for some reason, someone somewhere has decided to make that the case. So there we go. This paper's kind of annoyed me. Hope you found it helpful though. If you did, please leave a like, and if you want to see other OCR papers, then click on the card and it'll take you to the playlist. See you next time.